In this lesson, we will present two more examples of groups, the matrix groups over fields and the quaternions. So before we define a matrix group over a field, let's first talk about what a field is. A field is the smallest mathematical structure in which we can do all the normal operations of addition, subtraction, multiplication, and division. So the real numbers, for example, are a common field that we're all familiar with. So we're going to have matrices with entries that are in a field, and this will form a matrix group. But first, let's give a more formal definition of a field. A field is a set F with two commutative binary operations. So we have addition and multiplication. We have addition and multiplication such that F along with addition forms an abelian group so the elements of the field are commutative under addition, and the additive identity element will be denoted 0 for a field, and 2, the non-zero elements of F along with the operation multiplication also forms an abelian group. With multiplicative identity 1. So we have two operations, addition and multiplication, that are both commutative. We have additive inverses, additive identity, and the non-zero elements of the field also have a multiplicative inverse. Thirdly, we have the distributive property A times B plus C equals A times B plus A times C. So we have this distributive law in any field. For any elements A, B, and C in the field F. So the non-zero elements of any field are denoted by F with an X in the exponent. So some common examples of fields include the real numbers, the rationals, the complex numbers, and a very important example is the set of integers mod p, where p is prime. In fact, this field of integers mod p is denoted by a bold F sub p, because this is such a common example of a field with a finite number of elements. And if we think back to the integers mod p, since every integer is relatively prime to p, every non-zero element of the integers mod p has a multiplicative inverse, so this forms a field. Now let's define some matrix groups over a field. Let F be any field then for a positive integer n, we define the general linear group of degree n denoted GL sub n of F. This group is the group of all n by n matrices with entries in F and having non-zero determinants. So this set of n by n matrices with entries in F with non-zero determinants is a group under matrix multiplication. So GLN of F stands for the set of all n by n matrices with entries in F with non-zero determinants. And this set actually forms a group. So if we let A and B be n by n matrices, with entries in F, then A times B is also an n by n matrix. And its entries are also in F. And since the determinant of the product A times B equals the determinant of A times the determinant of B, we see that if the determinant of A is non-zero and determinant of B is non-zero, then the determinant of the product is non-zero. So we can conclude that the general linear group is closed under matrix multiplication. So in general, we know that matrix multiplication is associative. And given any field F, we can define the identity matrix to be the matrix with all zeros except along the main diagonal, which will have the identity element 1. So we have the standard identity matrix, I, and every matrix with non-zero determinant has an inverse matrix. So every matrix A with non-zero determinant has an inverse matrix A inverse such that A times A inverse equals A inverse times A, which equals the identity matrix. So thus, the general linear group is a group. And since matrix multiplication is not commutative, we see that this general linear group of degree n is non-abelian. So let's look at a specific example of this important class of groups. GL2R is the set of all 2 by 2 invertible matrices with entries with real entries. So this is a set of all matrices of the form A, B, C, D, such that A, B, C, and D are real. And the determinant of A, which is the standard value AD minus BC, is non-zero. So the set of all invertible 2 by 2 invertible matrices with real entries. So recall the formula for the inverse of a matrix, a 2 by 2 matrix. So the inverse of a 2 by 2 matrix is 1 over the determinant, AD minus BC, times the matrix with entries D, negative B, negative C, and A. So you swap A and D, and you negate the elements, the entries B and C, and then divide each entry by the determinant. So specifically, for an example, the inverse of the matrix 4, 3, 3, 2 is 1 over 4 times 2 minus 3 times 3. So the determinant is negative 1 times the matrix 2, negative 3, 4. And so the inverse is the matrix negative 2, 3, 3, negative 4. There's a specific subset of the general linear group that actually forms a group itself. This set is called the special linear group of degree n, and it consists of all n by n matrices with determinant 1 and entries in a field F. So we're going to define the set SLN of F, so it's called the special linear group, to be equal to the set of all invertible matrices with entries in the field F, so all A in the general linear group, such that the determinant of A not only is it non-zero, but the determinant is equal to 1. So the special linear group of degree n and by the same reasoning, we see that the special linear group is a group under matrix multiplication. Really, the only difference is that we have determinants equal to 1, but if A has determinant 1 and B has determinant 1, then the determinant of A times B is 1 times 1, which is 1. So we see that the special linear group over a field F is also a group. So we'll see examples in the future of these matrix groups over fields. Now we'll mention another classical example called the Quaternions. The Quaternion group under multiplication is a finite group. It only has 8 elements, and is actually it can be thought of as kind of an extension of the complex numbers, but it is a classical example of a non-abelian finite group. So the Quaternion group under multiplication is defined by the set. There's 8 elements, so it has the identity element 1, negative 1 is an element. We have I, negative I, J, negative J, K, and negative K. So these are the 8 elements of the Quaternions, and the relations that these elements satisfy are first of all, the identity element is denoted 1. So any element times 1 will just equal that element. 2, if you multiply an element by negative 1, we still get this normal product. So negative 1 times A is the same as A times negative 1, which equals negative A for any element A in Q8. We have the standard multiplication by 1 and by negative 1. But thirdly, this relation completely determines all the other products in the Quaternion group. So I squared is equal to J squared, which is equal to K squared, which also equals I times J times K, and all these products equal negative 1. So from this last relation, we can actually determine all the other possible products of elements in the Quaternion group. And as I mentioned, the Quaternions are not abelian. For example, if we look at this last relation, ijk equals negative 1, if we multiply both sides of that equation by k, well, we can deduce that I times j actually equals k, but j times I will actually equal negative k. And again, these products can be deduced from the third relation above. So we see that ij does not equal ji, so Q8 is non-abelian. So this is an interesting example of a non-abelian group of order 8. This group was first discovered and described by Hamilton in 1843, and this group actually has modern applications in computer graphics with three-dimensional rotations. And there's other examples where this group is used to prove identities or prove statements